Now to get this started, I want us to look back at example 1 from the previous lesson. You may need to flip back in your notes, but if you do, you'll find that our function was x plus 1 over x squared minus 4, and this was the graph. We worked really thoroughly to get this graph, okay? And so what we're going to do is we are going to answer some questions regarding a rational inequality by looking at this graph, okay? Let me now ask you some questions regarding some rational inequalities with respect to this graph. So watch this. All right, let's do one at a time. The first rational inequality I want you to consider is x plus 1 over x squared minus 4, which we already graphed right here below, right? Below, this is the graph of this rational expression or rational function. When is this rational expression strictly less than 0? Now, we have answered similar questions like this with polynomial inequalities and quadratic inequalities. This symbol can be read as when is the graph below the x-axis? So then all we really need to do is look at the picture and we can see from left to right that it is below the x-axis for this interval here, which is negative infinity all the way to negative 2. And then it's also below the x-axis from negative 1 all the way to positive 2, right? From negative 1 all the way to positive 2. And then that's it. Not this at all, because this is above the x-axis. So then the answer in interval notation would be from negative infinity to negative 2, parenthesis, union from negative 1 to positive 2. I can highlight this for you on the graph. It'll be from negative infinity all the way to negative 2, and then again from negative 1 to positive 2. Now, we have parentheses on all of our endpoints because the inequality is strict. Okay, that's it. That's the answer to the question. All of the hard work is already done because we have the graph. Now notice what was the most important part of this graph in order to answer the question is the vertical asymptotes and the x-intercept. All right, let's answer another question with regard to this graph, okay? Now we have the same rational expression. When is it less than or equal to 0? Now please understand that this symbol still means when is it below the x-axis. So it's the same exact question, except you and I, when we were solving polynomial inequalities, you and I would take this non-strict inequality, right, and put brackets on the endpoints. Basically, put brackets on these endpoints. That would be the only difference. Well, that's true here in this context as well, except we have to be careful about something. I can put a bracket at negative 1 because that's an x-intercept. A bracket on negative 1. But I cannot put a bracket on negative 2 or positive 2. Even though this is non-strict, I cannot include negative 2 or positive 2 because that's where these vertical asymptotes are. In other words, the function is undefined at negative 2, undefined at positive 2. So although this is non-strict, I cannot put a bracket on negative 2 or positive 2. So basically, when you're working with rational functions, right, rational expressions, if you have a non-strict inequality, you can only put a bracket on an x-intercept. And the x-intercept here is negative 1. So the answer here is the same as before. The only thing that is changing then is there's a bracket on your x-intercept of negative 1. All right, so this inequality would only change the bracket on negative 1, or the symbol, right? The symbol on negative 1. All right, you probably figured I would ask these two questions next. X plus 1 over x squared minus 4 greater than 0, greater than or equal to 0. Now, I'm still talking about the same graph, okay, because this is still the same expression. Now, both of these, greater than 0, greater than or equal to 0, can be interpreted as when is the graph above the x-axis. All right, so I want us to look at when is the graph above the x-axis. Again, because we have the graph, most of the work is done for us already. It's above the x-axis from, I'm going to highlight it, from -2 to -1, and then it's above the x-axis again from +2 to +infinity. Okay? All right, so then the answer to this first one is from -2 to -1 union from +2 to +infinity. This would be the answer, right? From here, right, from -2 to -1, and then from +2 to +infinity. I have parentheses on all of my endpoints because this is a strict inequality. Now let's go to this answer. It's still the same question, when is it above the x-axis? The only difference is this is non-strict, so I can put a bracket on my x-intercept only. The x-intercept is -1, so basically my answer will be the same as before. It'll be the same as this, just a bracket at the x-intercept. So the answer would be -2 to -1, bracket, union, parenthesis 2, all the way infinity. Again, you can only put, you have to put parentheses at -2 and +2 because those are your vertical asymptotes. Okay, now let's recall example 2. This is from the previous lesson. I'm trusting that you took really thorough, organized, neat notes, and you can reference this graph here. We worked hard at getting this graph in the previous lesson. Now that we have the graph, we can answer some inequality questions for this function. So watch this. Okay, so the question is, when is the graph of this function below the x-axis? Below the x-axis. All right, I'm going to highlight it for us. It's below the x-axis from the x-intercept of 4/3 all the way to, it's getting infinitely close to this vertical asymptote, which is happening at x equal to -1/2. So it's below the x-axis from -1/2, because this is approaching -1/2, all the way to 4/3. Now, because this is non-strict, I can put a bracket on my endpoint as long as the endpoint is an x-intercept. I cannot put a bracket on a vertical asymptote. So it'll be from -1/2, let's put a parenthesis there, all the way to 4/3, let's put a bracket on 4/3. So from -1/2 all the way to 4/3, let's put a bracket on 4/3 because this is a non-strict inequality. I want you to notice again what were the key features, the important features of our graph in order to answer the question. And this is what we're about to say was also true in the previous question. The important features of our graph that helped us answer this question and give the answer in interval notation were two things: the vertical asymptote and the x-intercept. So it seems as if when you are solving a rational inequality, all we really need from the graph are those two things. What are your vertical asymptotes and what are your x-intercepts? What are your vertical asymptotes? What are your x-intercepts? At these two locations in the graph, a vertical asymptote or an x-intercept, those are the two locations in the graph where you're going from being below the x-axis, watch this, to being above the x-axis. An x-intercept, you're below the x-axis, and then you are above the x-axis. Below the x-axis, now you're above the x-axis. It's at x-intercepts where you transition from being negative to being positive. A vertical asymptote as well. You transition from being positive to being now negative down here. So from now on, when we solve a rational inequality, all we really need to do is find the vertical asymptotes and the x-intercepts, and then we can answer the questions. All right, check this out, everybody. Solve this rational inequality, 2x squared over x squared minus x, strictly greater than 0. Now, let me be very clear. If you wanted to, you can get a detailed graph of this rational expression by finding the vertical asymptotes, the end behavior asymptotes, the end behavior asymptote, the x-intercepts, the y-intercept, determine whether the graph crosses the end behavior asymptote, and so forth. Everything that we were doing in the previous lesson. And once you have a detailed graph, a detailed picture, then you could figure out, okay, when is the graph above the x-axis? Above the x-axis. But what I'm telling you right now is a shorter way is you don't need the end behavior asymptote. You don't need the y-intercept. All you really need is what are the vertical asymptotes and what are the x-intercepts? With those two pieces of information, I can figure out when is this graph above the x-axis. All right, now you're going to want to be careful here with this rational expression. It can be factored, right? The denominator as x times x minus 1. Correct, everybody? And what you can do at that point is you can divide out a common factor of x. So then that would give you 2x over x minus 1 is strictly greater than 0. Okay? And so what you want to do is be careful because now when I find my vertical asymptote, right? I'm referencing this simpler expression, and I'm going to take its denominator, which is x minus 1. I'll set it equal to 0 and solve, and I see that I only have one vertical asymptote, x equal to 1. Now, let's not forget what we learned in the previous lesson, and that is whenever there is a common factor that divides out, like in this example, the x is divided out, then that means there's a hole in the graph. Now, the common factor that got divided out was x, wasn't it? So take that common factor that got divided out, set it equal to 0, and you can see right away, oh, there's a hole in this graph when x is equal to 0. Now, when I plug this value in, right, I will find out the ordered pair at which there is a hole. So here I go, I'm going to plug it in, all right? So I have 2, I'm plugging in 0 there and there. So I'm going to have 2 times 0 over 0 minus 1. This is just 0 over negative 1, which is 0. So in other words, 0, 0, which is the origin, that's the origin, there is a hole in your graph, which means the function is undefined. The function's undefined when x is 0. That's very important. Okay, so I told you that really all you needed was the vertical asymptotes and the x-intercepts to solve this equation, or to solve this inequality, excuse me. So now let's find the x-intercepts, okay? Now you find your x-intercepts by taking your numerator, which is simply 2x, and you set your numerator equal to 0 and you solve. When you divide both sides by 2, you get x equal to 0. So your x-intercept is the origin. Wait a minute, that's where the hole is. So the graph is going through the origin, but at the origin, there's a hole, which means the function is undefined at that location, okay? I'm gonna go ahead and box that. But don't forget, this is also where the hole is, all right? Okay, watch this, everybody. Here's your x-axis, all right? You know that there's an x-intercept at 0. So there's 0. And then you know there's a vertical asymptote at x equal to 1, okay? What this does, it splits your x-axis into 3 intervals, here, here, and here. There's 3 different intervals here, right? What I want you to do is choose a value from each of these intervals, and I want you to plug it into your function. Now, don't forget your function is 2x over x minus 1. And the question is, when is it above the x-axis? All right? So here we go. Choose a number, please, that is less than 0. How about -1? So that's 1 test point. And then choose something between 0 and 1. How about 1/2? And then something greater than 1. How about 2? It can be anything greater than 1. It doesn't have to be 2. It doesn't have to be -1. Anything less than 0, okay? All right, these are my test points from each of those intervals. And what I'm going to do is I'm going to plug these test points one by one into this expression. And all I'm doing, guys, all I'm doing is determining whether my output is greater than 0. That is to say, am I getting something positive? All right, now I'm just going to follow the sign here. I'm not going to do all of the work. When I plug in -1 for x, my numerator is negative, okay? A negative numerator. And when I plug in -1 in the denominator, -1 minus 1, that's negative. And a negative divided by a negative is a positive. So that means this interval is positive. What that means is, without having to graph the entire function, what that means is to the left of 0, the graph will be positive. That is to say, to the left of 0, the graph will be above the x-axis. Now let's do 1/2. When I plug in positive 1/2, I don't want to do all the arithmetic, just follow the sign. You're plugging in a positive number, so the whole numerator is positive. Now the denominator, you're going to get 1/2 minus 1. That's going to give you a negative result. And a positive divided by a negative is a negative. So that means between 0 and 1, the graph is negative. That is to say, between 0 and 1, the graph is below the x-axis. Finally, let's plug in 2. When I plug in positive 2, my numerator is positive. And when I plug in positive 2 in the denominator, my denominator is 2 minus 1. That's positive as well. And a positive divided by a positive is a positive. So, to the right of 1, the graph is above the x-axis. Now remember, you're trying to figure out when is the graph of this expression above the x-axis. Well, you just found it. It's above the x-axis in this interval and in this one. So then your final answer in interval notation would be from -infinity all the way to 0, union from 1 all the way to positive infinity. This is the final answer. I have parentheses on 0 and on 1, the endpoints, because this inequality is strict. All right, here's our brand new example. When is this rational expression less than or equal to 0? Let's be very clear. They're asking you, when is this rational expression, when is the graph of this rational expression below the x-axis? All right, very good. So, in order to answer that question, let us find two things, vertical asymptotes and x-intercepts. Now, there won't be any holes in this graph this time around, so it'll be a little less work, okay? And there's no holes in this graph because there are no common factors between the numerator and denominator, even after you factor, okay? All right, here we go. Let's find our vertical asymptotes, okay? And the way you do this is by taking your denominator, setting it equal to 0, and solving. All right? Now this factors as x minus 3 times x minus 3 is equal to 0. That is to say, x minus 3 is equal to 0. X equal to 3 is your one and only vertical asymptote. The only other thing that you need to find are the x-intercepts. The way you find your x-intercepts is by taking your numerator only, setting it equal to 0, and solving. So you can see that your x-intercept is the origin, 0, 0. All right, 0, 0. Now, what I'm going to do is I'm going to draw my x-axis again, okay? Let me show you this. Here's my x-axis. Okay, there's my x-axis, and I have an x-intercept at 0, and I have a vertical asymptote at 3. I have 3 different intervals here, 3 different intervals. I have the first interval to the left of 0, second interval between 0 and 3, and a third interval to the right of 3. Now, let us not forget the question. I'm going to scroll up on the page, okay? The question, and maybe it's worth writing down again. The question, if I can, there it is. The question is, when is the graph below the x-axis? Now, remember, when you're looking for something that's below the x-axis, that means you're looking for something that is negative. Below the x-axis means you're looking for something that is negative, negative. All right, so keep that in mind. All right, here's our x-axis. And what we want to do is choose a value from each interval. Choose a test point. Any number that's less than 0, any number that's between 0 and 3, and any number that's greater than 3. Okay guys, I've identified 3 numbers that I would like to choose. I chose -1, I chose +1, and I chose +4. Now, let's keep this in mind. We're going to plug these values into your rational expression. Now, do you remember the rational expression, the denominator factored like this? When we were finding the vertical asymptotes, we factored the denominator. I can do better than this, everybody. Instead of writing x minus 3 twice like this, I will choose to, now stay with me, plug my test points into this, x minus 3 quantity squared. Now remember that you are not doing all of the arithmetic. All you really want to know is, am I getting something negative or am I getting something positive after plugging in each of these test points? Now, another thing to keep in mind, the denominator is being squared. So I don't care what you plug in for x and then you take 3 away. It doesn't really matter because once you square it, it will always be positive. So the denominator is always positive. All right, here we go. We're going to plug these test points in. Now, we just said the denominator is always positive. So I'm going to do that for each one. Positive, a positive denominator. Now, when I plug in -1 in the numerator becomes negative. And a negative divided by a positive is negative, so this interval is negative. When I plug in +1 in for that numerator, the numerator is positive, and a positive divided by a positive is positive. Finally, when I plug in +4, I get a positive over a positive, which again is a positive. Now, let's not forget what it is we were looking for. We were looking for when is the graph below the x-axis. That is to say, when are your outputs, your function values, when is the graph negative? And so it's negative here in that interval only. So therefore, your final answer is from negative infinity all the way to 0. Now, let's be careful here. Should we be putting a bracket or a parenthesis on 0? What do I do? Well, let's look at the original inequality, shall we? The original inequality is up here. There it is. The original inequality is non-strict. That means I'm supposed to put a bracket on my endpoint as long as it's an x-intercept, right? You cannot put a bracket on a vertical asymptote. You can only put a bracket on an x-intercept when this is non-strict. Okay, everybody? It's non-strict, so I can put a bracket on my x-intercept. Now, the number I have in my answer is 0. Is 0 a vertical asymptote, or is 0 the x-intercept? It's the x-intercept. So because this, because this is an x-intercept, I can go ahead and put a bracket on that endpoint, all right? So this is my final answer. Okay, everybody? Here's our next one. When is this rational expression greater than 0? When is this rational expression above the x-axis? When is this rational expression positive? So then if this is above the x-axis, if that's how I interpret this, then we're looking for when is the function positive. Keep that in mind. Okay, everybody, we have to find the vertical asymptotes and the x-intercepts. Now, there is no common factor between the numerator and denominator. The denominator doesn't even factor, and neither does the numerator. So let's find the vertical asymptotes and the x-intercepts. All right. The vertical asymptotes are found by taking your denominator, setting it equal to 0, and solving. However, when you solve by subtracting 2 and then taking the square root of both sides, you get plus or minus I root 2. Because these are non-real solutions, these are imaginary solutions, you do not have any vertical asymptotes. Now, your x-intercepts are found by taking your numerator and setting it equal to 0 and solving. So I'm going to add 3 to the right, and then I'm going to divide by 4. So your one x-intercept is 3/4. So 3/4. Keep that in mind, everybody. 3/4. So all I'm going to do is draw my x-axis, and here is my x-intercept. That's it. That's all I have labeled on my x-axis. I don't have any vertical asymptotes. And so what I'm going to do is I'm going to choose a test point from each of these two intervals. I do have two intervals, to the left of 3/4 and to the right of 3/4. So let's choose some test points. Something less than 3/4, how about 0? Something greater than 3/4, how about 1? Now let's remind ourselves what we're plugging these values into. All right, here is the expression that we're plugging these values into. Now we're looking for when is it greater than 0, that is to say when is it positive. Now keep this in mind, everybody. The denominator will always be positive. Because you're taking a real number, you're squaring it, so that's going to be a positive answer. And then when you add 2 more units to a positive answer, this is all positive. So no matter what happens, the denominator is positive. No matter what happens, the denominator is positive. Okay, when you plug 0 in, the numerator is negative because it's 4 times 0, which is 0, minus 3, which is minus. So it's a negative divided by a positive, which is a negative. So then this interval here is negative. Now when I plug in the number 1, I get 4 times 1 minus 3. That's going to end up being positive. And a positive divided by a positive, of course, is positive. Now, do you remember what we're looking for? We're looking for when is the graph positive. So now you can see it's positive in that interval. Now, because this is strict, I must put a parenthesis on this endpoint, 3/4. So the final answer is from 3/4 to infinity. This is the final solution set. Okay, 2 more examples here for us, guys. This one is going to be interesting. Now, if you look back on all of the examples that we've done so far in this lesson, on the right-hand side, there's always been a 0. This is the first time where you do not have a 0 on the right. So, in order to get a 0 over here on the right, which is what you want, I'm going to have to move this whole term to the left using subtraction. Okay, so I'm going to subtract that term from both sides, and that will give me 2x over x minus 1 minus x over x plus 1 is strictly less than 0. This is very important, everybody, that you want a 0 on the right-hand side. The next thing you want is you want to combine these two rational expressions to be one rational expression. The only way you can actually combine these two using subtraction is if these denominators are the same. So you're going to have to get common denominators here. Notice that your LCD is x minus 1 times x plus 1. So then each of these denominators need to be x minus 1 times x plus 1. So this expression is going to have to be multiplied in the numerator and the denominator by x plus 1. This expression is going to have to be multiplied in the numerator and the denominator by x minus 1. All right, so now, let me move this up for us, shall we? Now, the numerator here turns out to be 2x squared plus 2x. That's me distributing this 2x here, okay? And then distributing a negative x here gives me negative x squared, be careful with your signs, plus x. And all of this now is over the LCD, and this is less than 0. Now, combining like terms in the numerator gives you 1x squared plus 3x over the LCD. Okay, I'm going to go a step further here, and I am going to factor the numerator all the way. So this is x times x plus 3 over x minus 1 times x plus 1, strictly less than 0. All right, everybody, this is what you and I wanted. You and I wanted a 0. Listen carefully. You and I wanted a 0 on the right-hand side, and we wanted just one rational expression on the left. Only one term only, and we needed common denominators for that. Okay, so this was definitely more work, right, than the other one so far, okay? You need a 0, and you need one rational expression on the left. Now, here we go. In order to answer their question, and the question is, when is this rational expression below the x-axis? We need two things: vertical asymptotes, x-intercepts. All right, so less than 0 means below the x-axis, which means you're looking for when is the graph negative. Now, the vertical asymptotes, I take my denominator and I set it equal to 0, which means you set each factor equal to 0 and solve, and you have two vertical asymptotes, 1 and -1. The other thing that I need are the x-intercepts. Now, I find the x-intercepts by taking my numerator, setting that equal to 0, and solving. So then when I take my numerator and set it equal to 0 and solve, I find two x-intercepts, 0 and -3. Now let's be very clear as to what's an x-intercept and what's a vertical asymptote, all right? So here we go. We're going to remember that we're looking for when is it below the x-axis. We're looking for negative values. Negative, okay? Keep that in mind. Also keep in mind this expression because this is what we're going to plug our test points into. All right, here we go. Here is my x-axis. All right, everybody, here's my x-axis, and I have my important points here. A lot of times we call these critical values or critical points. Just a reminder here, this is an x-intercept, this is an x-intercept, and then -1 is a vertical asymptote, +1 is a vertical asymptote. What we're going to do is we're going to choose a test point from each of these five intervals. We're plugging them into this expression, follow the sign, and see what when the graph is less than 0, that is to say, when is it negative? Okay, everybody, that's our goal. When is it negative? All right, everybody, I chose my test points. Now, keep in mind, you can choose whatever test points you want as long as the test points are in these intervals, okay? And they're not these critical points that we have here, okay? So I chose -4, I chose -2, I chose -1/2, I chose +1/2, and I chose +2. I'm plugging each of these values into this expression and following the sign. All right, here we go. When I plug in -4, this first factor is negative. This second factor, -4 plus 3, will become negative. So you'll have a negative followed by another negative. And in the denominator, you'll have, after plugging in -4, you'll have this will be negative, and so will this one. Okay, I'm not even going to do all the arithmetic. I'm just following the sign. So 2 negatives in the numerator, 2 negatives in the denominator. This will all turn out to be positive, will it not? All right, so this is positive. That means to the left of -3, the graph will be above the x-axis. Let's go for -2 now. Plug -2 right here, this will be negative. And when you plug -2 in here, this will be positive. Negative and then a positive. Now going to the denominator, when you plug in -2, this factor is negative, and so is this one when you plug in -2. Count how many negatives you have. You have 3 negatives, 1 in the numerator, 2 in the denominator. An odd number of negatives means the whole fraction will end up being negative. So between -3 and -1, the graph will be below the x-axis. All right, now let's plug in -1/2. The first factor, now I'm talking about this, the first factor, the second factor, and then the factors in the denominator, okay? So the first factor will be negative. The second factor in the numerator will be positive, right? The denominator will give you a negative factor followed by a positive factor. I count 2 negatives, so this whole fraction will be positive. Now we're plugging in +1/2. When I plug in +1/2, the first factor is positive. The second factor is positive. Downstairs in the denominator, you'll have something negative followed by something positive. This whole thing will be negative. So then between 0 and 1, the graph dips below the x-axis. Finally, let's plug in the number 2. The first factor will be positive. The second factor will be positive. The factor down here will be positive, and this will be positive. So all positive. Cool. So we did not have to graph this entire function in order to figure this out. Now remember, you're looking for when is the graph below the x-axis. That is to say, when is it negative. So then the intervals you're looking for are this interval and this interval. Now because this is strict, you have to put parentheses on all of your endpoints. parentheses on all of the endpoints. Hey, by the way, if this inequality was non-strict, watch this. Can you watch me do this? If it were non-strict, it's not right now, but I'm just saying, if it were non-strict like this, you could put a bracket, but only on the x-intercepts. Only on the x-intercepts, which are -3 and 0, right? You would still put a parenthesis on -1 and +1 on the vertical asymptotes. But in this problem, your inequality is strict, so everybody gets a parenthesis. Therefore, this would be your final answer. All right, everybody? The graph is below the x-axis between -3 and -1 and between 0 and +1. And we did not have to graph the entire function in order to figure that out. All right, we made it to the last example. It's x plus 3 over x minus 2 is greater than or equal to 1. Now, just a reminder, we don't want a 1 over there. We want a 0. So what I'm going to do is I'm going to subtract 1 from both sides so that I can get a 0. All right? When I subtract a 1 from both sides, I get x plus 3 over x minus 2 minus 1 is greater than or equal to 0. Now, that's good. That 0 is good. But what I need to do now is combine these two expressions so that I only have one rational expression, not two. Okay? So notice that the LCD is x minus 2. So what I'm going to do is I'm going to rewrite the number 1 as a fraction whose denominator is x minus 2. So in other words, I'm going to rewrite the number 1. I'm going to rewrite the number 1 as x minus 2 over x minus 2. After all, whenever you divide an expression by itself, that's 1. So all of this is 1. Okay? And now the denominators match. So now I can combine these two and say, we got to be careful here. See this negative? It has to be distributed. Let me write that down, or at least show it. Distribute that negative. Man, that's so important. Be careful. So this becomes x plus 3 minus x plus 2 all over x minus 2 greater than or equal to 0. Let me move this up. This leads us to, notice do you guys see it? I just saw it right now. These x's cancel. And so all you're left with in the numerator is the number 5 over x minus 2 greater than or equal to 0. Man, that seems pretty convenient, right? So let's focus on this. Now this is what we worked hard to get. A 0 on the right and only one fraction or rational expression on the left. Now, what we need are the vertical asymptotes and the x-intercepts. Now let us not forget that greater than or equal to means above, greater than or equal to 0 means above the x-axis, which means you're looking for when is the graph positive. That's very important. All right, vertical asymptotes are found by taking the denominator, setting it equal to 0, and solving. So you only have one vertical asymptote. Now let's find the x-intercepts. The x-intercepts are found by taking the numerator, okay, taking the numerator, setting it equal to 0, and solving. Now this is a problem because 5 will never be equal to 0. This doesn't make sense. That's a contradiction. So this means you do not have any x-intercepts. So this saves us actually a lot of time because you only have one critical value, one critical point, and that is the vertical asymptote at 2. So you only have 2 intervals here, to the left of 2 and to the right of 2. So what we're going to do right now is we're going to choose some test points. Choose something to the left of 2, how about like 1 or something, or 0, and then choose something greater than 2, how about 3. And you're going to plug it into this expression and you're looking for plus signs. Okay, everybody, so here we go. I chose 0, which is less than 2. Again, choose anything you want less than 2. And I chose 3, which is greater than 2. Now, I'm going to plug them in here for x. Notice that the numerator is always positive. It's positive 5. It's fixed at 5. And remember that you're looking for greater than or equal to 0, so you're looking for plus signs, right? Let me put that next to this. So this means you're looking for plus signs, all right? Here we go. When I plug in 0, the numerator is always positive. But when I plug in 0 in the denominator, I just get negative 2. So then a positive divided by a negative is a negative. So this interval here is negative. Now let's go for the next test point. The numerator is positive because it's fixed at 5. The denominator, when you plug in 3, you get something positive. A positive divided by a positive, we know, is positive. So remember that you are and I are looking for when is this rational expression greater than or equal to 0, which means above the x-axis, which means when is it positive? It is positive right here, right? From 2 to infinity. Now, I'm about to write my answer, but we have to be super careful right now. This inequality is non-strict. That means we should put a bracket on our endpoint, which is 2. However, you can't do that here because 2 is a vertical asymptote. The graph, the function, is undefined at x equal to 2 because this is the value that makes your denominator 0, right? So you have to put a parenthesis on 2 even though this is non-strict. You could have put a bracket on 2 if it were an x-intercept, but it's not. You don't have any x-intercepts. So because this is a vertical asymptote, I have to put a parenthesis on 2 and then all the way to positive infinity. This is my final answer. Okay, I don't know about you guys, but I'm tempted to put a bracket on 2 because I'm trained to think that whenever I have a non-strict inequality, I put a bracket on my endpoint. And that's true as long as that endpoint is an x-intercept and 2 is not an x-intercept. It's a vertical asymptote. You always put parentheses. Regardless of this inequality symbol, you always put a parenthesis on your vertical asymptote. Okay, this is the last example, and this is the answer for it, all right? I hope you learned a lot. I hope that the big takeaway here is that when you're solving a rational inequality, all you need are the x-intercepts and the vertical asymptotes. And then you just choose test points from each interval and follow the sign.